Hey guys, here are our notes for 3.4 day 2. All right, also what's going to go along with this homework assignment, or with this notes, is the homework assignment page 135, numbers 2, 6 through 10, and then 12. Okay, and that'll also be in Google Classroom, but I figured I'll start, or try to start remembering to add that to the notes so that you guys can see that ahead of time. All right, example 1, write the, why are we not out of focus? Focus! Write the area of an equilateral triangle as a function of the side S. Okay, well, the area of a triangle is area equals 1/2 base times height. But they want us to write it in terms of the side S. So that means they don't want B's and H's. They want everything to be an S. So this is an equilateral triangle. Equilateral means all three sides are congruent, and they want all three sides to be a length S, obviously, because it's equilateral. They want us to use S as the variable. And in an equilateral triangle, we know that all three angles are 60 degrees. But I need to represent something with the base. Obviously, the base I can call S, but I need something to represent the height of this triangle. So when we split an equilateral triangle equally in half, we get a 30, 60, 90 degree right triangle. That's a special right triangle. So back in Math 2, I think, is when we originally show this to you guys. Basically, the short leg is always a length of A. The long leg is always A times the square root of 3. And the hypotenuse is always 2 times whatever the short leg is, so 2 times A. So we're going to be using this to help us with this. So I want to find the height, and I know that this whole bottom side is S. So half of it would be half of S, so S over 2. So since this is across from the 30-degree angle, that means this is my short leg. So my long leg is going to be the short leg times square root of 3. So S over 2 times the square root of 3. So S square root of 3 over 2 pretty much. I know you can't see that. Let me zoom in a little bit. Okay, so now I know what to plug in. Area is going to equal 1/2 the base, the whole bottom side of that triangle is a length of S. The height of that triangle is S square root of 3 over 2. So when I multiply straight across, I'm going to have 1 times S square root of 3. So that is S squared square root of 3 all over 2 times 2 is 4. So the area equals S squared square root of 3 all over 4. Okay. We need that because it builds on from there. Now in part B, it says to find the instantaneous rate of change of the area A with respect to the side S. So find the derivative, basically, of that equation that we just came up with. Instantaneous rate of change means we're finding a derivative. So we're going to take A equals this. Now I'm going to rewrite this because square root of 3 over 4 is basically my coefficient. So I'm going to write it in front of the S squared this time. I just rearranged it, but it still means the same thing. But now it's easier to see when we take a derivative, we drop the power in front and we knock it down 1. So A prime is going to be, we're going to drop down that 2 in front of the square root of 3 over 4. And now S is to the first power. Well, 2 goes into 4 twice. So the derivative then is the square root of 3 over 2 times S. And there's our derivative. All right, letter C, it says evaluate the rate of change of A at S equals 2 and S equals 10. Well, we found the formula for the rate of change, the square root of 3 over 2S. So now we're just going to plug in an S value of 2 and an S value of 10. So I'm using the derivative formula to plug in a 2. So A prime of 2. So that'll be square root of 3 over 2 times 2. The 2's cancel, and we get square root of 3. Then for the derivative with an s value of 10, we'll have the square root of 3 over 2 times 10, and 2 goes into 10 5 times, so I will have 5 square roots of 3. Easy peasy. Oh, birdies. They're fighting over the food. Mando's hogging it. Letter D says, is S, not is, that's supposed to say if S is measured in inches and A is measured in square inches, what units would be appropriate for dAds? So the derivative of the area with respect to the side S. Okay. Well, area is measured in square inches, so dA would be measured in square inches. And S is measured in inches, so ds would be measured in, inches. So basically their units are the same even if we're taking a derivative of them. All right, example 2 says a square of side length S is inscribed in a circle of radius R. So that means we have a square, and I'm going to try to draw this as best as I can. And it's inside a circle. So when a square is inscribed in a circle, that means it's all 4 corners are touching the edges of that circle. And since we have a circle, we know it'll have a radius, and that radius will be R. And since we have a radius extending from the center of the circle to the corner of that square here and here, that means this is going to be a 45-degree or a 90-degree angle, which means that that angle in the corner there is split in half because it's also a 90. So half a 90 is 45. So this is a 45, 45, 90 special right triangle that is being made here. It says write the area A of the square as a function of the radius R of the circle. So what is area of a square? Well, the area of a square is a side squared, side times side. Okay. Well, we need to figure out how to rewrite that so it's in terms of the radius of the circle. So in terms of R. So that's why I drew this in here. Well, we know back in the day, back in Math 2, we learned the special right triangle 45, 45, 90. So when the sides are A, because this is an isosceles right triangle, we have A, the hypotenuse will always be A square root of 2. Okay, so if here we have a 45, 45, 90 right triangle, and since the legs are both a length R, that means the hypotenuse would be R square root of 2. Okay, I think we have enough here. So that means the side length of that square is a length of R radical 2. So that means we can write the area as, instead of S, we can plug in an R square root of 2 and square that. So that means that both terms inside the parentheses are going to get squared. So our area is going to equal, well, whenever you square a radical, the number inside gets to come out, and then the R squared is going to be squared. So 2R squared is representing the area of the square inscribed in that circle. Letter B, it says find the instantaneous rate of change of the area A with respect to the radius R of the circle. So that means we are again finding a derivative. So we have the area formula there. Now let's go ahead and find its derivative. So A prime, we'll use power rule. Oops, pen got away from me. Drop the 2 from the exponent down next to the 2 that's already there. 2 times 2 is 4, so that'll be a 4R. So the derivative is 4R. And then it says evaluate the rate of change of A at R equals 1 and R equals 8. So that means we just got to plug in a 1 and an 8 into our rate of change formula, the derivative there. So A prime of 1 would just be 4 times 1. So that would be 4 whatever units. We don't know the units for this problem. And then a prime of 8, well, 4 times 8 is 32. So 32, whatever units they are. If R is measured in inches and A is measured in square inches, what units would be appropriate for dA dr? Well, the derivative of A, if A is measured in square inches, and the derivative of A is in square inches. And over dr, well, if R is in inches, then dr is also in inches. So inches squared over inches. Flip it over. And it says, let me zoom out, the coordinates S of a moving body for various values of t are given. Plot S versus t on coordinate paper, well, on this graph, and sketch a smooth curve through the given points. Okay, so it's S versus t. So t is standing for the time in seconds. It says that right here, t seconds. S has to do with the number of feet. So my y-axis is in feet. Now, if I look at my x values, they're 0 all the way up to 4. So the highest it's going is 4. So I definitely have plenty of room here, and I don't want them to be too squished up because I see I have halfway marks. So I'm going to let this be 0, and every 2 lines will be a whole unit. That way I'll have that dash mark in between to mark the halfway points. For the y's, I see that the lowest number I have is 12.5. The highest number I have is 50. So I probably want to count by 5s if I want to get up as high as 50. 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. Okay. All right, so let's start plotting these. So my first one is 0, 12.5. Well, 12.5 happens to be halfway between 10 and 15. And then 0.5, 26. So about right here. And then 1, 36.5. So about right here. And then 1.5, 44. And then 2, 48.5. So about right here. And then 2.5, 50. And then it comes back down. 3, 48.5. And then 3.5, 44. And then 4.0, 36.5. What helps is that it's a parabola, so I know that these are pretty symmetrical. Trying my best to draw a smooth curve. That's not too bad. Okay, so here are my plotted points. This is an original graph. This is not a derivative graph. So let's make sure that we remind ourselves this is the original. It's the OG. Okay. All right, so it says in part B, assuming that this smooth curve represents the motion of the body, estimate the velocity at t equals 1, at t equals 2.5, and at t equals 3.5. So we're going to be estimating the velocity, okay? So since we're estimating, we're going to be finding an average rate of change. Average rate of change, which means we're going to be using the slope formula, okay? So that means we need to look at the rate of change or the slope between the surrounding points. So the points surrounding 1, the points surrounding 2.5, and the points surrounding 3.5. Okay, so we'll start with t equals 1. So for t equals 1, we're going to look for the surrounding points. Okay, well, at 1, the surrounding points around it are 0.526 and 1.544. So these are the surrounding points around the 1. So 0.526 and 1.544. And we're going to plug them into the slope formula. You should write that down just because this is your notes, so you remind yourself what you're doing and how you're getting to these answers. Okay, so the velocity at 1 second is going to be equal to approximately, so y2 minus y1, so that would be 44 minus 26 over x2 minus x1, that's 1.5 minus 0.5. So 44 minus 26, I'm not going to trust myself to do math in my head right now, even though it's easy math. 18 over 1.5 minus 0.5, that's easy. It's just 18. So this is 18 feet per second. Notice that this is positive. So that means this is the part of the curve. Well, obviously, at 1 second, this is the part of the curve where it's going up. Going up that downward facing parabola. So it makes sense. All right, then for t equals 2.5, we'll start that next. Let me move this up a little bit. Where is 2.5? Notice 2.5 is the top of that peak. That's the vertex of the parabola. So let's think about that. If it's the vertex of this downward facing parabola, that means that when we have a horizontal tangent, what's the slope going to be? Well, so the slope is of a horizontal. And slopes of horizontal lines are 0. So that means that v, the velocity at a time of 2.5 seconds, is going to equal 0 feet per second. Because that's its turning point. It's going to switch directions. So it's going to slow down to not moving, and then it's going to come back down. All right, and then the last one, for t equals 3.5. 3.5 isn't a vertex again, so we have to do what we did for t equals 1. We need to find the surrounding points. So at 3.5, the surrounding points would be 3 and 48.5 and 4, 36.5. So 3, 48.5 and 4, 36.5. So the velocity at 3.5 is going to equal, use the slope formula, y2 minus y1, so 36.5 minus 48.5 all over 4 minus 3. Well, 36.5 minus 48.5 happens to be a negative 12, so it's negative 12 over 1. So this is negative 12 feet per second. It's negative, so that means it's going in the negative direction. So that means this is when it is going down. Okay, which makes sense. So if we look at our graph at a time of 3.5, we're up here. And yeah, this is when we're starting to head down the parabola there. And that's it. Have a good one, you guys.